So I had talked about carbonyl compounds, and I want to pick up with the last one in the category we talked about, and specifically amides. And so talking about NH2 over here, in other words, a primary amide. That's primary. That would be a secondary amide. We'll just say R prime. Tertiary amide. So in all of these compounds, we're going to see the carbonyl band. And as I mentioned last time, because the nitrogen is donating in electron density into the carbonyl oxygen, the CO bond is weaker than most other carbonyls, and we're typically talking about 1650 to 1690. In addition to that, and sometimes this gets referred to as the amide 1 band. And in addition to that, you're going to have a number of other features that may clue you in that you have an amide. So for example, a primary amide is going to have 2 NH stretches. Why 2 for a primary amide?
There's 2 hydrogens attached to the nitrogen.
2 hydrogens, okay, that's part of it. But what specifically do we know about when we have 2 groups and stretch attached to the same atom or nearby? We saw this, for example, with methylene groups, and we also saw it in acid anhydrides.
Symmetric and asymmetric.
Bending stuff.
What's that?
The bending stretches.
Well, we'll get to the bending. Those are weaker, lower in frequency, but these are stretches.
Symmetric and asymmetric.
Yeah, asymmetric and symmetric. So that's the whole feature of coupled vibrations. And so those, if you have a primary amide, and we'll take a look at secondary amides in a moment. Of course, tertiary amides don't have an NH stretch at all. But those are pretty distinct. And they show up in that region above 3,000 wave numbers. And often IR spectroscopy involves kind of reading various clues together, how things look, the shape of various bands. So for example, for our primary amide, if you're as the in solution, in other words, where you're not hydrogen bonded, and let's just say we're looking, say from, I'll just say about 3,500 to 3,000. If you're not hydrogen bonded, you're kind of going to see 2 bands, and they may look something like this, about 3,520 and about 3,400 wave numbers, as sort of the way you might expect them to look. We often run IR spectra in the solid state. Often you'll make either a KBR pellet or apply the amide, apply the compound to the attenuated total internal reflectance crystal, the detector, or the sample holder. And so if they're hydrogen bonded, then they're going to be shifted to lower wavelengths and broadened. And so you might see something like this, maybe one band like so, and another band like so, maybe about 3350 and about 3180. These numbers aren't exactly carved in stone, and we'll take a look at some real amides in a moment. But the idea is sort of being able to recognize what your patterns look like and how things look. When we talked about carboxylic acid, I meant carboxylic acids. I mentioned they like to form hydrogen bonded dimers, that they're set up to hydrogen bond in a ring. And it's the same type of phenomenon with primary amides. Just to refresh your memory, we can think of the nitrogen here as sp2 hybridized. In other words, there's a good degree of partial double bond character, so it's nearly flat and conjugated to the carbonyl. And so it's sort of set up nicely to hydrogen bond. Like so, and that tends to broaden out the stretching. It's not quite as prominent or quite as strong hydrogen bonding as carboxylic acids, but it's still pretty significant. And if you ask for my least favorite compounds to chromatograph, carboxylic acids, primary amides, primary amines are all pretty lousy on silica gel chromatography just because of hydrogen bonding and poor separation.
James, before you erase, can you restate the difference between the top spectrum and the bottom spectrum, the difference between those two?
Right, so this is solution, and this would be typically neat, usually a solid.
Thank you.
Let's just say solid, because usually we'd be talking a solid, but basically not in solution. Other questions at this point? These are good questions.
Can that hydrogen bonding region be more prominent for the solution one? Like carboxylic acid, does it go wider?
They go sharper because, so you get more coupled vibrations when you're hydrogen bonded, because now you're not only getting coupling between these two, you're also getting coupling across the hydrogen bonded ring. So in carboxylic acids, remember, it's just terrible. Carboxylic acids end up sort of starting at about 3,500 and going to about 2,500 and sort of having this blobby band with maybe your CHs sort of poking out. So this would be a typical RCOOH. The amides aren't quite as bad as that, and the coupling isn't quite as severe. For secondary amides, you only have one NH. So again, we're talking something like this. You only have one NH, and the NH stretch, none of these numbers are exactly carved in stone, but let's say about 3,400 to about 3,500 in solution. In other words, not hydrogen bonded. And in the solid state, maybe about 3,300. In the solid state, even though you can't form that ring structure, you have a very high concentration of your molecule. And so the molecules are going to hydrogen bond together. And you'll probably see, and we'll see an example of this just in a moment, and they can form long chains. You probably see some combination of free and hydrogen bonded stretches. And you'll see it looks very distinct from, say, an alcohol or a carbon or a carboxylic acid. So in addition to this, was it Partho who mentioned bending?
Franco did.
Ah, okay, Franco. Yes, you do get bends. So primary and secondary amides have the NH bends. And just as we saw in the case of CH groups, where the stretching frequencies were up at about 3,000 and the bending frequencies were down at 1,400, in the case of NH groups, again, the bending frequencies are substantially lower than the stretching frequencies. And so the NH bend is usually at about 1,500 to 1650. And this gets a special name. It's called the Amide 2 band. We wouldn't have named the other one Amide 1 if there wasn't a reason, but it might be on top of the Amide 1 band. And remember, the Amide 1 band is the carbonyl stretching frequency. So this is probably a good opportunity to look at some real spectra. And I think I sent out this handout last time. Didn't I send out a second handout? So I'm not going to resend this. And what I'm going to do is, if technology allows me, I'll share my iPad with you. All right. Can you see the IR spectra here?
Yes.
Great. All right. So this is sort of a cool example, and this is, I believe it's from Nakanishi's book, which goes into, as I said, maybe more detail than you'd typically want. But I thought this was a fun example as a springboard for a couple of reasons. So he gives us in this problem that we have a compound. Let's see my tools here. We have a compound that contains a tert-butyl group. It has a molecular formula of C6H13NO, and he asks us to identify the compound. Who has an idea of what that compound might be? Take a couple of moments to think about it. And this is in chloroform solution. Let me stop sharing my screen and then whoever wants to comment. Carissa, was it you who wanted to show something? No.
Han.
Ah, okay. So what you have here is a primary amide with 1, 2. So it's a 5-carbon chain or 6-carbon chain primary amide.
Yes.
So let's get that up on the whiteboard here. What do people think? Does that match the problem as given?
Gotta have a tert butyl, right?
We gotta have a tert
Ultraviolet. Yes.
tert butyl. So tert butyl group is of course CH3, CH3, CH3 on a carbon.
So I have this structure.
Uh-huh. Let me, you know how to share your, okay. All right, so now we're getting maybe a little closer. So what do people think of this option? Let me throw another piece. All right, let me throw another piece of information into the picture here. So I'm going to share my screen again. All right. So same compound in a KBr pellet. And so now we see a slightly different pattern. I told you these features are not carved in stone and they depend on context. So let me give you another reasonably useful piece of information. This solution is probably not too dilute. And I can tell you that if the solution were more dilute, we would expect, if here's our band at 3,400, and here's that other band at 3,300, we would probably expect that band to be more prominent compared to the other band. So this is what I would say is dilute. So does that help influence your thinking on this?
Is it terbutylamide with methyl on one side?
Yeah. Tert-butylamide with methyl on one side and tert-butyl on the other. Exactly. So we're seeing, so let me draw out the structure, and I don't think we could easily determine between the two possibilities. So I'll just tell you tell you which of the two possibilities it is. And then we'll use that as a springboard to discuss the features that I've drawn out. All right, so the structure over here is tert-butyl acetamide. And what we're seeing over here, it's in chloroform solution, but you have mass action and more concentrated. You have a free, you have more of a hydrogen bonded NH stretch. And so you have some hydrogen bonded and some free. This is your free NH stretch. Maybe your molecules are even forming chains or dimers. As you get more dilute, you have much less hydrogen bonding. So your hydrogen bonded NH stretch at 3,300 is weaker. Then you have, this is your carbonyl, your so-called amide 1 band. And this is your NH bend, your so-called amide 2 band. So these are some of the typical features you might see in an amide. And then in chloroform solution, I mean, in a KBr pellet where you basically have tiny crystals of your compound interspersed with potassium bromide as a matrix, now you see primarily your hydrogen bonded NH stretch. And here again is our carbonyl. And here's our NH bend.
Isn't the KBr pellet supposed to get rid of the H bonding?
Not at all. Let me stop sharing. So in KBr pellet, which these days is maybe falling more out of fashion with ATR, what you do is you grind up a few milligrams of your compound, maybe 1 milligram. I think here they said 3 milligrams, and mix it with, usually I'd mix it with 100 meg of KBr. They use 200 megs of KBr. Grind them very fine so that the granularity of your solid is smaller than the wavelength of light. In other words, that your particles are a fraction of a micron in size, or at least just a micron or 2 microns in size. Then your light passes through them, but you've still got tiny particles of your compound. So it's not dissolved or dispersed in the KBr in a way where the molecules are separated. In chloroform solution, the molecules weakly self-associate. If your solution is strong, you have more of them self-associated. If it's weak, you have less self-associated. So thoughts, other thoughts or questions on this?
Can I see the labeling of the second graph again?
The what? Sure, you can.
Sure.
So I didn't catch what you said, Mark. So what did you want to see?
I think he just wanted to see this again so he could jot down your notes.
Ah, excellent.
I got a question though. How
All
do we
right.
know if the terp butyl group is attached to the nitrogen or if it's attached to the carbonyl carbon.
I would, other than having a reference spectra, I would be very hard pressed to determine whether it was tert-butyl acetamide or pivoyl or methyl amide. You know, in other words, whether the methyl were on the nitrogen or the tert-butyl were on the nitrogen. So the other thing I liked about this example is, and I saw somebody said, oh my goodness, there's a formula. And I thought that's also another nice springboard to discuss degrees of unsaturation. And so, yeah, we have a molecular formula here, and I wanted to tell you, A, what you can do, and B, what I actually do. So if you like equations, you know, it's incredibly useful to know the degrees of unsaturation, right? Degrees of unsaturation is the number of double bonds plus rings. And so if you're a person who likes formulas, you can say the unsaturation number, degrees of unsaturation, is the number of carbons minus the number of hydrogens divided by 2 minus the number of halogens divided by 2 plus the number of nitrogens divided by 2 plus 1. And you could say, okay, we have 6 carbons, 13 divided by 2 hydrogens, no halogens, whoops, that's a minus sign, no halogens, 1 nitrogen plus 1, and you come out with equals 1. Personally, I never can be bothered with this. I always just look and say, okay, well, I understand halogens count as hydrogens. Silicon, if you have silicon, counts as another carbon. Okay, I say, if this were an alkane, it would be CnH2n plus 2, but we have a nitrogen, so we add 1 more for a nitrogen. So that's my thinking on this, is basically, okay, well, it would be C6H14, H15 if it were saturated. And oxygen doesn't count, but we're C6H13NO, so it's 1 degree of unsaturation.
I'd like to make a plug for future in the course. Degrees of unsaturation becomes very, very useful during NMR. So it's useful to practice this with any chemical formulas you come across in the early problem sets.
I would agree, absolutely. And I think do we have it on our worksheets as one of the things that we ask people to fill out, James?
The degrees of unsaturation formula, you mean?
Yeah.
Oh, degrees of unsaturation for the Silverstein problems. Yes, I'm pretty sure it is.
Yeah, and that's to guide your thinking and to get you in the habit of good thinking. It's probably one of the most useful things you can have to guide your thinking. And I will add one comment that for salts like RNH3 plus Cl minus, this doesn't work. But an oxygen sulfur, count is the same. Phosphorus counts as nitrogen in trivalent phosphorus compounds. Pentavalent phosphorus becomes a little more tricky depending on what your compound is. But anyway, a very useful thing. All right, I want to show, were there any questions on degrees of unsaturation at this point? Who's gotten that concept already in your undergraduate courses or in other courses? Okay, so most of you have seen that concept.
I have a quick question about the degrees of unsaturation.
Yeah.
If you have a benzene ring, because it's a ring and there's 3 bonds, is that 1 degree of unsaturation?
4 degrees of unsaturation. So benzene, C6H6, and as I said, my thinking is always if it were an alkane, it would be C6H14. So it's 8 hydrogens shy, and that leads to 4 degrees of unsaturation.
James, could you do me a favor really briefly and just draw cyclohexane and straight chain hexane? I think it's helpful to visualize why closing a ring creates a degree of unsaturation.
You want the hydrogens in there, or are you good without them?
I think it's good without them. So what I'd like to draw attention to is if you were to create a new bond between the terminal ends of the straight chain cyclohexane, you would need to remove 2 CH bonds in order to create a new carbon-carbon bond, and removing that hydrogen equivalent is removing a degree of, or adding a degree of unsaturation to the ring.
Very good.
The way I visualize it.
So often when I'm working with a set of spectra, let's say I have IR spectra and carbon NMR and proton NMR spectra, I might be looking at several things at once. Maybe I even have the molecular weight of the compound. And I'm trying to piece together various things. And I say, wait a second, I see a double bond in the C13 NMR spectrum. I see a carbonyl in the IR spectrum. There are at least 2 degrees of unsaturation here. And maybe I count up the number of carbons from the C13 NMR spectrum, and maybe even the number of hydrogens from the proton NMR spectrum. And then I'll start to say, well, wait a second. Okay, we're still 16 short on the molecular weight. There's got to be an oxygen in there. I'm not seeing, whatever, or there's got to be another oxygen. It's an ester, or there's an ether in there. So often it's a sort of a puzzle solving to come up with the molecular formula. All right, I want to move on to amines. Amines are similar to amides, but I'll say weaker. But the NH stretches are weaker, much less prominent, particularly for secondary amines. So primary amines, honestly, if you can't keep all the numbers straight in your head, it's really virtually the same, but a slightly different look. So there are going to be 2 bands for a primary amine, and those bands would correspond to about 3,500 and 3,400 for the free amine, and about 3,400, a little lower in frequency, and 3,300 for the H-bonded amine. In other words, often that would be neat. You'll also see an amide bend, an NH bend at about 1,600 wave numbers. So right on the edge of the fingerprint region. For a secondary amine, so R, NH, R prime, then we're only typically going to see 1 band, slightly lower in frequency, let's say. So this is 1 NH stretch, I should say. Slightly lower in frequency. Let's say about 3,300, or 3350 to about 3310. Probably ballparks it. And I'll tell you from personal experience, if your secondary amine has any size to it, if it's a couple of hundred molecular weight, it is really, really hard to pick out. So what I'd like to do again is to share my iPad screen and continue in our handout. And the reason I wanted to do this here is I think this is a nice example of a real amine. And I'll just tell you what each of these amines are. So this is butylamine. And you can see this is neat. In other words, it's the pure sample applied probably to a sodium chloride salt plate. And I wanted to point out the features here. So here's our NH bend right on the edge of the fingerprint region, or at least I guess I'm calling the fingerprint region 1400 to 600. But let's say it's right on the edge of where I draw an imaginary line, or maybe not imaginary, and say, all right, I'm going to primarily look at things above 1600. And then here we see our NH bends, our NH stretches, and they're the symmetric and asymmetric, or asymmetric and symmetric. And it's all, essentially all hydrogen bonded. And what I wanted to contrast this to is the shape of an alcohol and the strength of an alcohol. So by comparison, what I've put over here is butanol. And you can see the OH stretch here, again, this is neat. The OH stretch here at about 3340 is stronger and also broader. It's pretty hard to miss an alcohol. It's a lot easier to miss an amine. And this particular amine, I'm making it, shall we say, easy for you, in the sense that the amine is very small, so you've got a lot of NH2 groups in your sample. If this amine were, say, 40 carbons in size instead of 4 carbons in size, then the intensity of this NH2 stretching band would be about 10-fold lower. In other words, it would be really, really subtle. And this is important because we're probably not going to go up to compounds that are 40 carbons in size. They're just a little bit big for most of the work that we're doing. But we'll often go up to compounds that are 20 carbons in size. And so it's very, very easy to miss an amine NH stretching band. Questions, thoughts? All right, so another thing you might encounter might be ammonium salts. Put simply, if you're working up a reaction with an amine and you're under acidic conditions, you might be crystallizing out the ammonium salt. Ammonium salts, so we're talking RNH3 plus, you know, X minus, or perhaps R2NH2 plus X minus. They are super ugly. You know, I often say that a carboxylic acid is the ugliest thing you're going to see in the IR spectrum. Well, ammonium salts are even uglier than carboxylic acid. So it's the same sort of thing of this big, fat, sort of broad band with maybe some features. But now you're probably picking up about 3,200 and sort of getting onto this whole band. And then you're going to go down maybe to 2,500 or 2,000, somewhere around there. And it is just not pretty in the IR spectrum. So I'll say ugly like a carboxylic acid. Let me show you a few more and then we'll look at some real examples. All right, nitriles, since we're talking about all sorts of nitrogen-containing compounds, nitriles are carbon triple bond nitrogen, are another common functional group. The CN stretch is about 2250. About 2250 wave numbers. Sharp. And it's always surprising to me that it's not super strong. It's sort of weak. We'll call it weak to moderate. That region of the IR spectrum around 2000 is unusual because there's not that much that appears here. And so it's easy to see, but because it's small and because sometimes other things might come there, like I said, if you somehow had deuterochloroform in your sample, it might be easy to miss. Nitro compounds, another common functional group. Nitro compounds, two bands, one at about 1500 to 1600, so right on the edge of the fingerprint region, and then one at about 1300, and they tend to be strong. What are the two bands? Why do we have two bands for a nitro group?
Symmetric and asymmetric stretching?
Symmetric and asymmetric, or asymmetric and symmetric NO stretches. Yeah, there are two resonance structures for a nitro group, and I guess I'll write them vertically. And it's not one, it's not the other. So two resonance structures. It's both at the same time, right? That's the nature of resonance. Put simply, the bond between nitrogen and oxygen is halfway between a single and a double bond in strength. So where many of our double bonds are occurring, say 1700 or 1600 for a carbon-carbon double bond or a carbonyl double bond, we're talking about slightly lower frequencies, and we're talking about coupled vibrations. And I should point out that if you have a carboxylate salt, it's the same thing. Your carboxylate salt, as a matter of fact, it's isoelectronic with a nitro group. Your carboxylate salt isn't a double bond and a single bond. It's a bond and a half and a bond and a half with two resonance structures. So your carboxylate anion has two bands as well. One's at about 1500 to 1600, and one's at about, or I'm going to give you a slightly more accurate number here. Let's say 1650 to 1550 for one, and about 1400 for the other. Same idea, asymmetric and symmetric stretch for your carboxylate.
I have a question. You said how it's symmetric and asymmetric, kind of akin to the CH2s, right?
Yep.
CH2s, they don't have resonance, and this one does. And because these are equal in resonance, I thought they would not have any symmetric one or asymmetric one.
So the way you need to think about this, and I wouldn't generally draw bonds this way, you need to think about it as two equivalent bond and a halves, where you have minus a half charge on one, minus a half charge on the other. So it's actually kind of exactly the same situation as a methylene group, where now you have a single bond. And so it's just that we have a stronger stretching frequency than a single bond, but of course our reduced mass is different and the bond strengths are slightly different. But basically, yeah, so we have a bond and a half and a bond and a half, and it's still going to do that asymmetric stretch and the symmetric stretch. And I'm going to show you an example of a carboxylate salt. So again, on your handout, the next page of the handout. And so the next page of your handout is phenylalanine. So phenylalanine, you would think of as the carboxylic acid and amine, but it's really the zwitterion. So we have two of the features that we've just talked about here. We've got this big, broad ammonium stretching band. And then we have our carboxylate, and here's our carboxylate asymmetric. And then one of these over here, I'm not sure which one, is probably the symmetric stretch. All right, I want to wrap up, I think, today with a couple of more comments, and that should set you up pretty well to get everything reinforced with the homework. So the IR spectrum, of course, or the IR spectroscopy is useful for many, many different functional groups. And in fact, more than maybe will just exist in your usual sort of working vocabulary. And I keep coming back to the idea that you really need to learn how to read an IR spectrum, that it's not just about memorizing band strengths and so forth. You certainly need sort of a working knowledge. But as I was saying, you can spot a lot of interesting stuff So even if you don't necessarily know what it is per se, this region from about 2000 to about 2300 is really interesting because usually you're not going to see anything there with many compounds, except if you do, you're going to have many of your triple bonds. So we talked about acetylenes, we've talked about nitriles. If you're an inorganic or organometallic chemist, you'll see carbon monoxide there. But also you're going to have cumulated compounds. Compounds where you have a double bond connected to an atom and then a double bond. So like allenes, like carbon dioxide that we talked about, isocyanates, which incidentally are isoelectronic with carbon dioxide, isothiocyanates, which are going to come up in the homework problems. And so this region is worth having a look at. And then even if you don't know everything, you're going to have many double bonds and triple bonds from about many double bonds from about 1800 to 1300. So we've already talked about carbonyls and carbon-carbon double bonds, but I said, you know, you may never encounter an imine, or you might encounter an imine, but that would be a good place to look for it or to expect it. You may or may not encounter a nitroso compound. That would be a good place to look for it as well. And I guess as a final side note, since I wanted to just show you a couple of last things, aromatics, typically we're talking combination bands, which are going to be weak, involving the ring. Typically, we're going to be talking about 1650 to about 2000. And also, if you're looking at aromatics, I'll just show you, these are combination bands. You're also going to see the out of plane CH stretches, or CH bends rather, at about 675 to about 900. And these can be very, very diagnostic. And I'm just going to flip over maybe one pattern that I'd like you to pay attention for in the homework, because it's so characteristic. And again, I think I've taken this from Nakanishi's book. So this is, Nakanishi went through and sort of recorded all the patterns you see for various substitution patterns. For simple phenyl compounds, you may see this set of sort of 4 bands between about 2000 and about 1650. And then you could correlate with the out of plane CH stretches, CH bends. And let's see, oh, we'll skip this example. It's just an example of a hydrogen bonded OH, internally hydrogen bonded OH. I guess I'll draw it out really quickly. Just so you can fill out your handout. So internally hydrogen bonded OH over here, showing up at about 3190 versus a free OH over here for the meta compound, showing up at about 3370. The other thing, and I think I'll hint at this in the homeworks, and Appendix C of your IR chapter in your textbook gives a nice treatment of this. You can actually distinguish among alkene substitution patterns based on some of this CH bending patterns that you see in this same region. And I think one of the problems you have is 2-pentene. And so you might look at that and ask, is it cis-2-pentene or trans-2-pentene, or it may be octene. Anyway, take a look. it's fun to be able to go deeper than you need to go in IR spectroscopy, even if you've just seen it once. And I urge you to do that. Well, I should probably end today's class, but if anyone wants to stick around after class for questions, I would be delighted to do so. Chris, are you waving goodbye?
I have a question.
Yeah, try it.
I'm having a bit trouble understanding the degree of saturation. So the formula dictates that there is a increase in, like, I guess 1 degree in saturation, but what does that tell me in terms of making and predicting the structure?
That is incredibly useful because you're going to say, oh, wait, there's a degree of unsaturation. Whatever molecule I draw either needs to have a double bond or a ring, but not both. And so you say, oh, okay, is there a carbonyl? No, there's no carbonyl. Okay, is there a carbon-carbon double bond? Oh, there's no evidence of a carbon-carbon double bond. Maybe I have a ring in there. So it helps you start to focus your thinking. Or conversely, you may look and say, oh, is this compound, a carbon? If this compound does have a degree of unsaturation, it's a ketone or it's a carbonyl compound. I know it can't have a ring. So I know it's got to be a linear compound. So those would be things that would be very useful to know as you're starting to fathom your structures.
From a practical standpoint, the way the homework is written, once we've introduced mass spec as a concept, one of the first things you'll be doing for each problem is determining the molecular formula based on the mass spectrum. And so if you know how many degrees of unsaturation you have before anything else, then you go into the IR and the NMR expecting to see, sort of like what James was saying, how you learn to read an IR spectrum rather than just look for specific bands. You go in expecting to see either I'm expecting there to be some sort of ring or I'm expecting there to be some sort of carbonyl, but not both. That sort of problem solving.